thanks for clicking. Welcome to another Nargilus production. Today we're going to be talking about tangent line approximations. Okay, using the equation of a tangent line or the tangent line to approximate the value of a function. So it sounds pretty complicated, but to be honest, it's pretty simple. Everything basically you already know how to do. So let's get started and let's have a look. So the goal here is to approximate a function's value using a tangent line. Now, why would you ever think to do this? Probably not unless I told you that we're going to do it. Okay, there is some application to it, which you'll talk a lot about in Calc 2. The fact that you can go and approximate functions with higher powers, not just tangent lines, but parabolas and cubics and all sorts of things. But for now, we're just going to use tangent lines. So just so you understand, this process of tangent line approximations has a bunch of different names. You can call it linearization. You could ask to find the local linearization. You can find a linear approximation. Any one of those, tangent line approximation, they all mean to do exactly the same thing. Okay, so here's the idea. I'm going to have a curve. Let's say I'm going to call it f of x. And I could pick any point that I wanted to and draw the tangent line at that point. All right, pick a point, draw the tangent line. There it is. There's my tangent line. Okay. Now, if I wanted to, I could use this tangent line to approximate the value of the function f of x. Okay. Now, you might be saying, well, maybe, it would work, I guess, but it probably wouldn't work very well depending on where you are. And that's true. We're going to talk about that momentarily. So let's see how this all works, and then we'll go ahead and we'll discuss some of the finer details as well. So here's what I want you to do. I want you to write the equation of the tangent line, f of x equals x squared at x equals 3. Okay, that's all I want you to do. So let's take f of x equals x squared. I want the tangent line, so I have to find the derivative. The derivative of x squared is 2x. Okay, and then at x equals 3, so f prime of 3 would be 6. That's my slope, right? Then I need a point to go with it, so I'm going to have to take 3 and plug it into f. 3 squared is 9. There's my point, 3 comma 9. So now I have a point and a slope, so I can write the equation of the line. And all I'm going to write is y minus 9 equals 6 times x minus 3. Write it in point slope form. There's my equation of the tangent line right there. Okay. So now what I want to do is I want to use the tangent line that I just wrote up here to approximate f of 3.2 and f of 5. Now, could you find f of 3.2? The exact answer? Sure. Take 3.2 and plug it into x squared. And you get your answer. Take 5, plug it in, you get your answer. But I'm asking you to use this tangent line to approximate it. So to do that, to figure out we'll start with f of 3.2. If x is 3.2, then I have y minus 9 equals 6 times 3.2 minus 3. Y minus 9 equals 6 times 0.2. So 6 times 0.2 is 1.2. So y minus 9 equals 1.2. Y would be 10.2. So f of 3.2, our conclusion, is approximately 10.2. And again, we have an approximation symbol here. This f of 3.2 is not equal to 10.2. We know that. It's approximately 10.2. All right. Let's do the same thing at x equals 5, and then we'll kind of discuss some of the finer details. So y minus 9 is equal to 6 times 5 minus 3. So that's 2. 6 times 2 is 12. So y is 21. So f of 5 is approximately 21, which we know darn well is wrong, right? Because 5 squared is 25. All right. So what have we actually accomplished here? Let's take a look graphically at what we actually see. So here's a graph. Here's x squared. All right. And now let's say, I don't know, somewhere over here, this is 3. So here's my tangent line. This is where I'm going to build my tangent line at x equals 3. That's what I did up above. And I'm going to draw my tangent line here. There it is. Okay. And let me extend my graph a little bit here so I can kind of get a better look. All right. So hopefully you can see just based on the picture what's kind of happening here. If you want to approximate a value that's really close to the point of tangency where you built the tangent line, the approximation's probably going to be pretty good, right? Because if you're on this line and you built this line at this point at x equals 3, if you're at x equals 3.2, the line and the curve, the line and the parabola are not going to be very far from one another. Okay, they're going to be pretty close still. But the larger or the smaller or the further away you get from this point of tangency, the worse the approximation is going to be. Like you can already see it at x equals 5. You're only 2 units away from the point of tangency, but now you're 4 units away from the actual value. Okay, and the bigger you get, the larger the value you want to approximate with this line, the worse the approximation is going to get. Okay, so that's something that you need to understand. So when we ask you to approximate with a tangent line, we usually ask you to approximate it with a value that's very close to the point of tangency. All right. Now, we can also see that, for example, f of 5, when we evaluated it, we got 21, right? And the true value is 25. Take 5, plug it in here. F of 5 is actually 25. So the value of the tangent line approximation is under the actual true value. So let's discuss that a little bit. So how would we decide if the tangent line is going to be an over or an under approximation of the true value? Well, you actually already know this because you've worked with it before. And to be honest, it's actually in the definition of a couple of concepts that we talked about a little while ago. If I draw a curve like this, I had a parabola, right, that opens up, and I draw my tangent line, like I basically did in the last example, my tangent line is going to be an under approximation here. So the tangent line is an under approximation to the true value, right? Because the tangent line, you can see, is underneath the actual curve. So the y values that come out for this line are definitely going to be smaller than the y values that come out for the parabola. But what if I drew the graph like this? Now, if I want to draw a tangent line, pick a point, draw the line. This tangent line is an over approximation to the true value of the curve, right? The line, the values you get on the line are larger than the values that are on the parabola. So the question is, what is the difference between this parabola or this shape and this shape? And hopefully you can see that the difference is the curve f over on the left is concave up, but the curve f on the right is concave down. And if you remember, that literally was part of our definition for concave up and concave down. Tangent lines lie below the curve, tangent lines lie above the curve. So it makes sense that concavity decides whether the tangent line is an over approximation or an under approximation of that true value. All right, let's try one more. It's known that g of 4 is equal to negative 3, g prime of 4 is 2, and g double prime is 4. is equal to 7. Use the tangent line to G at x equals 4 to approximate G of 4.2 and decide if the approximation is over or under. Okay, so I want to write the equation of the tangent line approximation. I need two things to write the equation of a line. I need a point and a slope. So my slope is 2. We agree right off of here. And I have a point at 4 comma negative 3. So I can write the equation of the line, y plus 3 equals 2 times x minus 4. And now I want to approximate g of 4.2. So I'm going to put 4.2 in for f, or in for x. It's 2 times 0.2. So that's y plus 3 equals 0.4. So y is going to be negative 2.6. So that means g of 4.2 is approximately negative 2.6. Make sure you write your conclusion with that approximation statement. Very important. Okay, this is not the true value. All right. So now I need to decide whether or not that approximation is over or under. So really at this point, the only thing I haven't used is that. G double prime of 4 is equal to 7. What does that tell me? Well, I know G double prime is greater than 0. So what does that mean about G? If G double prime is 7, that means G is concave up. So my graph looks like that. If G looks like that, the line I draw is an underestimate to the true value of G. So this is an underestimate. Because G is concave up. And that's my answer. And that's all there is to this. You're basically taking something we already know, taking a bunch of things we actually already know, kind of piecing them together and making something new. Okay? And as always, thanks for clicking.